introduction for people who came in late. I'm Milica. I'm Digital on Twitter, if that's a place you hang around. I'm a contractor for Google. I write on web.dev about performance and developer tools. So if you have slow load times or poor application responsiveness, web.dev is the place where you can find advice on how to fix that. And if performance is something you care about, and I really think you all should, please come talk to me about problems you're facing and how we can help you solve them. I'm also a Mozilla Tech speaker. And I was an intern on Servo, which is a browser engine. Parts of Servo are what makes Firefox fast today. Servo is fast because it does a lot of things in parallel, and it can do a lot of things in parallel because it was written in Rust. Rust is this cool new systems programming language, kind of like C or C++, but with memory safety built in. So a while back, I got to learn a little bit of Rust, but I'm a web developer, and I really love the web, and did not want to move away from that. This was in 2017, when WebAssembly just came out in browsers, and being at Mozilla at the time, it was the perfect opportunity to learn more about it. So in short, WebAssembly is a way to run code that is not JavaScript in the browser. I'm going to tell you about how we came to this point and why we really need WebAssembly. I'll explain how exactly is it different from JavaScript, and what does it realistically mean for the future of web development. Chances are you came across WebAssembly already without even knowing it. I'll show you some cool examples and some really practical ones, so let's get started. In every browser, whether you use Chrome, Firefox, or Safari, code is interpreted by a JavaScript engine, which used to only run JavaScript. But what about C, C++, or Rust? JavaScript is not ideal for every task we want to perform. That's where WebAssembly steps in. You do not write WebAssembly. You compile other languages to it. But why would you want to do that? Why do we need WebAssembly? The shortest answer is performance. And there are many use cases where performance is really important, but I want to talk about one particular, and that's video games. So some of the very first WebAssembly demos were video games. In 2017, Unity Engine ported the game of tanks that you could play in the browser. And then last year, someone ported Doom 3 to the browser. And also in 2017, Epic made their Japanese garden demo in Unreal Engine 4 run in the browser. So this is a GIF, so it's a bit stuttery, but if you ran this in a browser, I promise you it would be smooth. And this stuff is very computationally intensive and requires careful memory management. So you have fluttering leaves, butterflies. All of this means that the browser has to calculate the positions of millions of pixels in each frame and render them to the screen. And video games in general implement physics, they have to coordinate audio and video, and they often implement artificial intelligence. That's a lot of work, and it requires a high degree of performance. The performance that's really hard to get from JavaScript. This is a screenshot of the first website ever that Tim Berners-Lee published over 30 years ago. At the time, web was just hypertext, text, and a little bit of links. JavaScript was invented at the time to bring some interactivity to the web. So it was designed to be easy to learn and easy to write. But it wasn't designed to be fast. Over the years, browser engines added optimizations in the way they interpret JavaScript. As it got faster, a list of things that you could do in the browser started expanding. You got new APIs, and things that were previously desktop-only started coming to the web. Gmail is the perfect example. When Chrome came out in 2008, the Gmail also came with it, because all the optimizations in the JavaScript engine made an application like Gmail possible on the web. So today, we all send emails from the browser, and we added documents, but still, there are areas where JavaScript performance is still a struggle. So video games were an early goal for WebAssembly, not because it was meant only for video games, but because being able to achieve that level of performance meant bringing many other applications to the web. Now, think about other cases where you use software outside of the browser that are not video games. For example, video editing, or maybe music production, or 3D rendering, virtual and augmented reality, CAD applications, image recognition, and the list goes on and on. But why would we want all of this on the web? Why is the web so attractive? To me, the web is kind of like magic. It just works anywhere. There's no download, there's no installation, and it has safety built in. Browsers have sandbox, which keeps code running in them from messing with your system. When you go to a website, you never think twice before clicking a link, but you wouldn't just download a random binary and run it on your computer. And my favorite thing of all is the ease of sharing on the web. Links are just clickable strings that you can put anywhere. And we all know that's not how app stores work. So web is really a universal platform. It makes your application available on almost any device. Today, even refrigerators can run browsers. And for us developers, this also means maintaining a single code base, and it makes the updates easy. Because of all of these things, we went from a small scripting language to this powerful platform filled with amazing applications. But until now, it was still fundamentally powered by a small scripting language that was not meant to do all of that in the first place. So what exactly does WebAssembly bring to the table? I'm going to focus on 3 things. That's speed, portability, and flexibility. Let's talk about speed first. WebAssembly is a low-level binary format. This is what it looks like. It's a bunch of numbers. It also has an equivalent textual format that you could technically write by hand, but really it's only meant for debugging. Binary representation is what's actually delivered to the browser. Now, binary files are much smaller than textual JavaScript files. They're faster to download, and this is especially important on slow networks. And JavaScript's textual format actually means that the browser has to parse it. And parsing is not really as simple as it seems. Transforming plain text to binary has quite a few steps. There's lexing, tokenizing, turning that into abstract syntax tree, and then turning that into binary. But remember the previous slide? WebAssembly is already a binary format. That means no parsing, just decoding, which happens much faster. Another difference is the type system. JavaScript is a dynamically typed language. When you type x plus 1, you don't really have to say what x is. It could be a number, it could be a string, a Boolean maybe, and you don't even compile that code, you just give it to the browser. This makes it fast and easy to write, but it also means that the browser has a lot more work to do. It has to compile and optimize your code, and it sometimes has to do it multiple times if it makes strong assumptions about the types. Now, WebAssembly, on the other hand, is statically typed, so the engine doesn't really speculate during compilation about which types is it running. And most of the optimizations actually happen when you compile the source code, so before it even gets into the browser. And another speed boost for WebAssembly is streaming compilation. So kind of the same way you can watch a YouTube video as it's being downloaded, browser can compile WebAssembly code as it's being downloaded. For smaller binaries, this practically means that by the time the binary is downloaded, it's ready to run. All of these things make WebAssembly fast, but it's not like JavaScript cannot be fast. The thing is, writing fast JavaScript usually involves a lot of effort, knowing the optimizations of different engines, and writing your code in a really specific way that works for those optimizations. And the thing with that is that these optimizations are not the same in every browser engine. So if you write your code for V8, Chrome's engine, it actually might run slowly in SpiderMonkey in Firefox. And another thing is that these optimizations change with time. If a browser changes the way they optimize JavaScript, your code might run slowly somewhere down the line. WebAssembly, on the other hand, gives you reliable performance, and that's what makes it so attractive. My second point is portability. How do you take things from one place to the other and have it just work? Portability was one of the main goals in designing WebAssembly, so let's go over that web design quickly. Just so we're all on the same page. Assembly typically refers to humanly readable languages that are similar to machine code. Machine code is what your processor understands, a bunch of numbers. Now, every high-level programming language has to get translated down to machine code in order to run on the processor. And different processor architectures need different machine codes and different assembly for each of them. Now, when you know the exact definition of assembly, it's obvious that even though it's called WebAssembly, it's not really an assembly language. That's because it's not meant for any specific machine. You write your code to run in the browser, and when code runs in the browser, you have no idea which machine it's going to run on. So WebAssembly is actually a language for a conceptual machine that's the least common denominator of popular real-world hardware. When the browser downloads WebAssembly, it can quickly turn it into any machine's assembly language. And to run an application on a device, it actually has to be compatible with device's processor architecture and operating system. This means that you have to compile your code for every combination of processor architecture and operating system that you want to support. That's a lot of work, right? But with WebAssembly, there's only one compilation step, and your code will run in every modern browser. This enables two really good use cases. One is porting legacy applications to the web, and the other is having a single code base for code to run on multiple platforms. C++ is a particularly good language for this use case because it's supported practically everywhere, including iOS and Android. Now, another exciting thing about WebAssembly is the flexibility that it brings. Until now, JavaScript was the only fully supported language on the web. Now, we as web developers can actually choose other languages too. And developers who weren't actually web developers, who did not know JavaScript, can now also write code for the web. These are people coming from vastly different backgrounds with different perspectives. I think this diversity of different perspectives will actually make the web more interesting. And another aspect of WebAssembly's flexibility is the way that it fits into your applications. WebAssembly compiles into modules that you can use in your applications that can communicate with JavaScript. This means that WebAssembly is not a replacement for JavaScript. It runs alongside JavaScript. Now, JavaScript is actually really good at a lot of stuff. It's very efficient at DOM manipulation, for example. So sticking to pure JavaScript is going to be both faster and easier in many cases. But because they work together, you can now write some parts of your app, like user interface in JavaScript, while having some specific performance-intensive part of your application written in WebAssembly. Or if you're having a performance bottleneck today in your application that you weren't able to solve with JavaScript, you can now use a specialized language to solve that problem. So really, it comes down to using the right tool for the job. Fully supported languages today are C, C++, and Rust, but many others are in the works, like .NET and Go. C# already shipped pretty decent support, and there's like really a long list of languages that are coming. One that's really interesting to me is AssemblyScript. This is a version of TypeScript that allows you compiling TypeScript programs to WebAssembly. Now, you can just take any TypeScript. It really has to be strictly typed for this to work. But still, I think this is really awesome because As a web developer, I'm much more proficient in JavaScript than Rust. And I really definitely do not expect other JavaScript developers to just drop what they were doing and go learn a new language. But with TypeScript and assembly script, this is something that we are all familiar with, and we can easily get started and have a feel for what kind of stuff can WebAssembly do. Moving on to how this actually works. You need a tool that will compile your source code to WebAssembly. Now, compilation step is something that wasn't really a thing on the web for the longest time, but with tools like Babel and Webpack, that's not so true anymore. So in WebAssembly world, there's Emscripten, which is used for C and C++. Rust has its own compiler, Rust Nightly, that can compile WebAssembly directly. And in Rust world, Vasin is a cool companion that can also package your modules for publishing on the web. And here's how exactly this goes. If we take Emscripten compiler, for example, it takes your source code, and what it gives you is actually a WebAssembly module and HTML and JavaScript files. It needs those HTML and JavaScript files because WebAssembly doesn't actually have access to web APIs. So things like DOM, WebGL, or WebAudio are not really directly accessible today. Even to get the output of your WebAssembly program on the page, you need to go through JavaScript. Now, HTML file loads that JavaScript boilerplate, and it allows you to display the output of your WebAssembly program in a text area or a canvas element. Now, in Rust world, Vasin Binding is a tool which makes this a bit easier, but still it's not the smoothest process. And there are a couple of more tricky things. It has only 4 types, which are all numbers, which means that if you want to pass a more complex data type string, for example, you have to encode it in an array of numbers and pass a pointer to it. It also doesn't have direct access to external JavaScript variables, which is a thing that will change pretty soon with WebIDL and reference type proposals. But really, today, good advice is to use WebAssembly to offload big chunks of work, resource-intensive tasks, for example, resizing an image or processing an audio stream. So you're all probably wondering, are people using this in production today? And the answer is yes. Let's see some examples. First thing I mentioned are open source libraries. And if you've ever uploaded a huge raw image to Facebook, it actually went through WebAssembly code, because Facebook is using this old C library called libjpeg, which is over 40 years old. But it does the job really well. And if you play anytime an audio file on Wikipedia, they also use an open source codec called Opus, compiled to WebAssembly. And George yesterday talked about face detection in the browser, and he mentioned computer version library called OpenCV. Parts of OpenCV have been compiled to WebAssembly, which enabled use of this C++ library directly in the browser with performance an order of magnitude faster than a similar JavaScript library. And another use case most interesting for JavaScript developers are hybrid apps, where only parts are running in WebAssembly. Squish is an app from Google for compressing images. It supports several compression algorithms, like MozJPEG, PNG, and WebP. Now, these algorithms are implemented in C++, compiled to WebAssembly. Then the resizing function is written in Rust, compiled to WebAssembly, and the rotation function is assembly script compiled to WebAssembly, while the UI is actually written in Preact. And this app is really fast. You can load it right now on your mobile phones if you visit squish.app. And big apps are using WebAssembly too. Figma is an interface design tool that runs in the browser. It allows designers to easily collaborate. It has a really powerful 2D rendering engine, which is written in C++, compiled to WebAssembly, but their user interface is actually written in TypeScript and React. And I mentioned you could port legacy apps to the web. One really good example is AutoCAD. This is a really old application that engineers use to make designs of electrical circuits or maybe floor plans. It's been around for 35 years, longer than the web itself. And they ported it to the web using WebAssembly without having to rewrite a single line of code in a code base that's probably hundreds of thousands of lines of code. And a really cool example is Google Earth, which came about 14 years ago. It allows you to zoom in on your home or stroll the streets across the world But in order to do that, you had to download it and install it on your computer. Because 14 years ago, this kind of performance was not available in the browser. But this year, they also ported it to browser using WebAssembly. And there are many more examples. Like, people are doing weird stuff. Someone ported Windows 2000 to the browser, so now we have an operating system in the browser. And yes, you can totally play pinball in it. Another fun example is Vasin Boy, a Game Boy emulator written in assembly script, which comes with the interactive debugger written in Preact. And there are many more examples. People are using WebAssembly to implement blockchain. I think Ethereum currency is doing that. There's a scientific visualization tool called Iodide, and many, many more things. WebAssembly is supported in all major browsers. That means over 87% of all global users. Now, this is really different from how things were in the past. Some of you maybe remember these images, like Flash and Java applets, but the younger crowd here probably has never seen them. And the reason for that is that these technologies are dead. So they were pushed by competing companies, and they ran as plugins. They were never really part of web platform. WebAssembly, on the other hand, has standards committee. All browser vendors are working together on implementing new features, and it's really a part of web platform, which will really ensure that it stays that way. Now, what are the benefits for JavaScript developers here? I think this integration will make JavaScript even more powerful because you get access to all the modules from all the different languages. I think JavaScript expanded in part because of NPM and ease of downloading other people's modules. But WebAssembly is also distributed in the same way. There are already over 600 modules of WebAssembly right on NPM. Now, what if you really don't think you're going to use it? You have absolutely no plans to make a video game or to write the next Photoshop. Well, you can still benefit from WebAssembly and from the speed boost that it brings through improved tools and libraries. This is already happening. Firefox DevTools and Webpack both use source maps library that was recently rewritten in Rust, which made it 11 times faster. And in framework land, React has features that could easily be rewritten in different language and made faster. Like its non-diffing algorithm could be easily parallelized in Rust and compiled to WebAssembly. There are also other things that WebAssembly can do. It is starting expanding beyond the browser. Now, initially, it ran inside engines, but really, it's an assembly language for a conceptual machine, which means you can create other runtimes that can run WebAssembly and work on different operating systems. Cloud providers like Fastly and Cloudflare are already doing that. So WebAssembly obviously works, but it's going to get even better. The stuff that lies ahead is full support for threading, which is already available in Chrome, but soon it's going to be re-enabled in Firefox too. And support for garbage collection will make bringing languages like Java or C# much easier to WebAssembly land. And another important goal is creating better debugging tools, which will enable source maps that will allow you to see directly your source code in the browser. And soon enough, you'll be able to import WebAssembly modules just by using a script tag. If all of this sounds interesting to you, how about you just try it out? If you want to poke around, there are a couple of web IDEs that do not require you to install any tool chains. One is WebAssembly Studio, and the other one is WebAssembly Explorer. Now, this is WebCamp, and I really want to say again that JavaScript is a great language. It's flexible enough to do almost anything, and it will still have its place in web development. Those few gaps that it cannot fill can now be filled with WebAssembly. WebAssembly is really not the end of JavaScript. It's a new beginning for the web. Thank you. OK, here are some links. OK, here you go. Links to learn more and a link for feedback. And really, thank you for your attention. If you have any questions whatsoever, I'll be right here because I ran over my time. But I'd really love to talk to all of you and just meet you and answer any questions that you might have. OK, thank you again.